In this video, we're going to be going over natural logs and logarithmic equations. So let's say we have ln of x, that's equal to log base e of x. If you have ln of x is equal to a value like y, if you take e and raise it to that power of y, aka what ln was equal to, that is just equal to the input that you had for ln, which is equal to x. So for example, if you have ln of 7 equal to x, you're going to raise e to the power of x, aka what it was equal to over here, and you're going to raise that to the power of x and set that equal to 7, which was the input of ln in the first place. Let's talk about the product rule. So if you have the natural log of a times b, you can take that and split it up and say natural log of a individually plus natural log of b. So for example, we have natural log of 6x is equal to natural log of 6 plus natural log of x. So the power rule is if you have a natural log of a to the power of k, and then you shift that k to the front. So then you have k natural log times a. For example, if you have natural log of x to the power of 3, that's 3 ln of x, because we just shifted that 3 outwards. The inverse rule is if you have natural log of e to the power of x, that's equal to x. So if you have e to the power of ln with an input of x, that is just equal to x, because the base of ln is equal to e. So that's going to cancel out. Now, the domain has to be greater than 0 for natural log, and the input of any of your logs. Let's continue with the quotient rule. If you have natural log of a over b, that's the same thing as taking the natural log of a individually and subtracting it from the natural log of b. So you have natural log of x divided by 5. That's the same thing as ln of x minus ln of 5. If you have the root rule, that's ln of the root of x is equal to the natural log of x to the power of 1/2. And you can take that 1 over 2 and shift that to the front with the previous rule we had, the power rule. And then we have 1/2 times the natural log of x. So for example, if you have natural log of the cube root of x, you can take that out, and then we have that raised to the power of x to the power of 1 over 3. Then you take that out, and then you shift that to the front. So then you have 1 over 3 times ln of x. We have the change of base formula, which is we have the log of base b is equal to the log of the ln of x, which is our input, right? Divided by the natural log of b, which was our base. So this is how we can rewrite logs using natural logs. And if you have ln of x, that's equal to log base b of x divided by log base b, taking input of e. And also, if you have log base b of x, that's equal to ln of x divided by ln of b. Now let's do some examples. So let's say we have log base 2 x minus 1 plus log base 2 x minus 3 is equal to 3. The first step we must take is checking the domain. So x minus 1 is something that's inside, so that has to be equal, or that has to be greater than 0. Adding 1 to both sides, x must always be greater than 1. Here we have another input, and the input always has to be positive. So x minus 3 must be greater than 0. Adding 3 to both sides, x must always be greater than 3. So this is going to be the more strict requirement for a domain. So this is the one we are going to use and always test our solutions against. Now let's say we had to combine our logs. So we're going to combine this into one large log. We have x minus 1 times x minus 3, and that's all equal to 3. So we're going to rewrite this in exponential form. We have x minus 1 times x minus 3, and we're going to take this 2, that is the base, correct? Because we say base, so that's 2, and then this is going to be the exponent. So that becomes to the power of 3. Now we can simplify this. This is equal to 8, and we can just multiply. So that's going to be x squared times negative 3x minus x plus 3, which is x squared minus 4x plus 3 is equal to 8. So then subtracting 8 from both sides, we get x squared minus 4x minus 5 is equal to 0. Now we can factor this. What multiplies to negative 5 but adds up to negative 4? Well, that's x minus 5 and x plus 1. So that's equal to 0. Now, using the zero product property, x is equal to 5, or x is equal to -1. Now let's check the domain for both of these solutions. So our requirement is that x has to be greater than 3. So we can see that 5 is going to be greater than 3, but -1 is going to be less than 3. Therefore, this is not a valid solution, and our only valid solution is x is equal to 5, because that satisfies our domain restriction. Now, for a second example, let's say we have natural log of x plus 2 minus the natural log of x minus 1 is equal to the natural log of 3. So we're going to check our domain first. X plus 2 has to be positive, so subtracting 2, x must always be greater than -2. Here, x minus 1 always must be greater than 0. So adding 1 to both sides, x always has to be greater than 1. So x is greater than 1 is going to be the stricter domain restriction and the one that we are going to test against. We're going to use the quotient rule. So ln x plus 2 over x minus 1 is equal to the natural log of 3. The quotient rule states that ln of a minus ln of b is going to be equal to ln of a over b. In this case, we can see that this is our top here, and then we have that as a, we have this as b, and that as b. So now all we have to do is we can recognize that natural logs are going to be equal to each other because they both are going to have the base of e, correct? So you can just cancel out and ignore those. We're just going to take x plus 2 over x minus 1 is equal to 3, that input of the other right side. So now all we're going to do is we're going to cross multiply. So 3 times x minus 1 is equal to x plus 2. So we can distribute. We have 3x minus 3 is equal to x plus 2. Now we can add 3 to both sides and subtract x from both sides. We're going to have 2x here is equal to 5. So we can divide by 2, and x is equal to 5 over 2. Our domain restriction was that our value has to be greater than 1, which is true here. So x is equal to 5 over 2 is a valid solution. Now let's do another example. Log base 4 x minus 1 plus log base 2 x minus 1 is equal to 6. X minus 1 has to be greater than 0. So x must be greater than 1. We're going to convert everything to base 2. And we can do this because log base 4 x minus 1 is equal to log base 2 x minus 1 over log base 2 input of 4. And we know log base 2 input of 4, this is going to equal to 2. So that means that we have log base 4 x minus 1 is equal to 1/2 log base 2 x minus 1. So we can substitute this in for log base 4 right here. We know that this is all equal. So now we can rewrite this as 1/2 log base 2 x minus 1 plus log base 2 x minus 1 is equal to 6 right here. So we're going to let u equal to log base 2 x minus 1. This is u substitution. So if we do that, for every place where we have this log base 2 x minus 1, we're going to substitute that in with u. So we have that right here, and we have that right here. So this is going to turn into a simple equation. 1/2 u plus u is equal to 6. So that's u is just a whole number, so that we can write that as 2 over 2u is equal to 6. 1 plus 2 is just 3 over 2u is equal to 6. So then we're just going to multiply by the reciprocal on both sides, 2 over 3 here. And we get that u is equal to 6 times 2 is 12 over 3 is equal to 4 as our answer. So u is equal to 4 though. However, that's not our final answer because we had u substitution. So this is only in terms of u for a solution. However, we want it in terms of x. So in our equation, log 2x minus 1 is equal to 4. We'll substitute in. We can rewrite this exponentially as x minus 1 is equal to 2 to the power of 4. So we have x minus 1 is equal to 16. And adding 1 to both sides, we get x is equal to 17. So we can see 17 is greater than 1. So this is going to satisfy our solution for our domain. Now, let's do another example. Let's say we have log base 2x squared plus log base 2 4 over x is equal to 6. So for our domain, we can see here we have x. So x must be greater than 0. Now, how about we expand this second log? So for this log, we can rewrite this using the quotient rule. We're going to have log base 2 4 over x is equal to log base 2 4 minus log base 2x. This is equal to 2 minus log base 2 of x, because this is the same thing as 2. It's 2 to the power of 2 is equal to 4. Now, we can rewrite our entire equation as log base 2x squared plus 2 minus log base 2x is equal to 6. So now we'll use some u substitution. Let u equal to log base 2x. So everywhere where we see log 2x, we can just substitute that in. So we have u squared plus 2 minus u is equal to 6, and u squared minus u minus 4 is equal to 0. Now this is going to be a quadratic, which means we can use the quadratic formula to find the solutions. So u is equal to negative 1 here, plus or minus the square root of negative 1 squared minus 4 times 1 times negative 4, all divided by 2 times 1. So we can simplify this, some arithmetic. We have 1 plus or minus 1 plus 16, which is 1 plus or minus the root of 17 over 2. And this is all equal to log base 2x, because we're substituting u back in with its actual value, log 2 of x, which is what we defined u as. So we have 1 plus the root of 17 over 2. And we also have a second solution, which is negative, because we got two solutions from our equation. Now we can rewrite these both exponentially. We have x is equal to 2 to the power of 1 plus the root of 17, all divided by 2. And here we have x is equal to 2 times 1 minus the root of 17, all divided by 2. So now we have to check our domain. And both of these answers, they're going to be positive. This is going to be positive as well, because when you have a power of 2, powers of 2 are always going to be positive. So they both will make x greater than 0. Now, let's do another problem. Let's say we have ln of e to the power of 2x minus 3e to the power of x is equal to natural log 10. So because both of the sides are natural logs, we can set the insides of the natural logs equal to each other. So e to the power of 2x minus 3e to the power of x is equal to 10. Now you can rewrite using substitution. We have e to the power of x in both of these terms, so that's convenient for us. We're going to let u equal to e to the power of x. So we can rewrite this as here specifically as e to the power of x times 2, which is going to become u to the power of 2. So this e to the power of x was u. Now, what we have in total is u squared minus 3u is equal to 10. So you can move 10 to the other side. You have u squared minus 3u minus 10 is equal to 0. So now let's just factor this. We have u minus 5 times u plus 2 is equal to 0. Zero product property, we get 0, u is equal to 5, or u is equal to negative 2. So let's substitute back in. We have that e to the power of x is equal to u. So let's return here with that. So e to the power of x is equal to 5, and e to the power of x is equal to negative 2. However, e to the power of x can never be negative. So we're going to reject that answer. Now we have this answer. We can rewrite this as x is equal to ln 5 by taking the natural log of both sides. If you take the natural log of both sides, ln, that cancels out. So you get x is equal to ln 5. Let's say we have e to the power of 2 ln x minus 5 e to the power of ln x plus 6 is equal to 0. So because ln x appears, we know that x must be greater than 0. So let's simplify using e to the power of ln x is equal to x. So we also know that e to the power of 2 ln x, we could rewrite that as e to the power of ln x squared. So we get e ln x is equal to x squared because that double e to the power of ln is going to cancel out because the base is e. Now our equation is going to become x squared minus 5x plus 6 is equal to 0. Now we can factor this and we get x minus 2 times x minus 3 is equal to 0. We get x is equal to 2 or x is equal to 3. Now we can check the domain for this. Both of these are going to be a positive number, so these are both correct solutions. Let's say we have log base 2 x plus 1 plus log base 2 x minus 3 is all equal to log base 2 4x plus 12. Let's check the domain for each of these. So first we're going to have x plus 1 has to be greater than 0, so x has to be greater than negative 1. We have x minus 3 is going to be greater than 0, so x has to be greater than 3. And finally, we have 4x plus 12 has to be greater than 0, so subtracting 12 from both sides, we get 4x is equal to 4x is greater than negative 12. Dividing by 4, x must be greater than negative 3. So our strictest requirement is going to be this one. So we're going to test against x is greater than 3. Let's combine our left side. We can write this as log base 2 x plus 1 times x minus 3. And this is all equal to log base 2 4x plus 12. Now we can set the insides equal to one another. We have x plus 1 times x minus 3 is equal to 4x plus 12. We can set them equal because the bases are equal to each other. Now, all we do is we're going to expand this. We have x squared minus 2x minus 3 is equal to 4x plus 12. You can just subtract 4x plus 12 or minus 12 from both sides. And this side is going to be equal to 0. So you have x squared minus 6x minus 15 is equal to 0. You can just use the quadratic formula now because you have a standard quadratic. 6 plus or minus the root of negative 6 squared minus 4 times 1 minus 15. And you can divide all that by 2. So this is equal to 6 plus or minus the root of 36 plus 60, all divided by 2. This is 6 plus or minus the root of 96 divided by 2, and this is 6 plus or minus 4 times the root of 6, all divided by 2. So after this, we can just divide that 6 by 2. We get 3 plus or minus the root of 2 times the root of 6. So let's check these solutions. We get that x is going to be equal to 3 plus 2 times the root of 6, and that's greater than 3. So that's valid. Now x is equal to 3 minus 2 the root of 6, that's going to be less than 3. So that's not valid. So our only solution is going to be this first solution. Let's solve our next problem. Let's say we have log base 5 x plus 4 plus log base 5 x minus 4 is equal to 2 log base 5 2x minus 8. So first off, x plus 4 must be greater than 0. So x must be greater than negative 4. Again, we have the same thing here, except x minus 4 must be greater than 0, so x has to be greater than positive 4. 2x minus 8 has to be greater than 0, so x must be greater than 4, because you add 8 to both sides, and then you have 8 divided by 2. That's equal to, so you have 2x here, divided by 2, Now, let's combine the left side. We have log base 5 x plus 4 times x minus 4 is equal to 2 times log base of 5 2x minus 8. So on the right side, you can use the power rule. We can take this and write this as log base 5 2x minus 8 is power of 2. So we're just going to move that up there. So we have this equality. We can set the insides equal to each other. Since we have the log of the same thing on both sides, the insides have to be equal to each other. So now we can expand. We have x squared minus 16 is equal to 2x minus 8 times 2x minus 8. So on this side, we're going to get 4x squared minus 32x plus 64. So now we're going to move everything to one side. Let's subtract x squared minus and add 16 here. And do the same thing on this side as well. So we get 0 is equal to 3x squared minus 32x plus 80. So now we can just factor. Because we have a 3 out here, we can just take out a 3. So we have x squared minus 8x plus, or actually you can just do 3x minus 20, x minus 4. So x is equal to, setting 3x minus 20 equal to 0 and x minus 4 equal to 0, you get x is equal to 4. You could add 20 to both sides, and you could have 3x is equal to 20. So then you divide everything by 3, and x is equal to 20 over 3. So we have to have that x has to be greater than 4, correct, for our domain. So 20 divided by 3 greater than 4, but x is equal to 4 is not greater than 4. So this is invalid. Our only solution is going to be x is equal to 20 over 3. Now, for our next problem, let's say, okay, do we have room? Room here. Natural log of x plus 3 is equal to 2 ln x minus 1 minus natural log of 2. So we have this. We have x plus 3 is greater than 0. That's going to be x is greater than negative 3. Here we have x minus 1 is greater than 0, so x has to be greater than 1. Our combined domain is going to be this one because it's stricter. Let's use the power rule. So we have 2 ln x minus 1. This is going to be the same thing as ln x minus 1 squared, because you can just put that 2 up there. So that is going to be our new expression, minus ln 2 is equal to natural log of x plus 3. Next, we can use the quotient rule. We have ln x minus 1 squared over 2. So we can set the insides of these equal because they both are going to be natural logged on either side. Cancel that out, cancel this out. So x plus 3 is equal to inside. Now we can multiply both sides here by 2 to cancel out that 2. So we have 2x plus 6 is equal to x minus 1 squared. And this is going to be equal to x minus 1 times x minus 1. We have x squared minus x plus 1, x squared minus 2x plus 1. So let's move this here. And 2x plus 6. Let's subtract 2x 6 from both sides. Let's do the same over here. So we have 0 is equal to x squared minus 4x minus 5. And you can factor here. You have x minus 5. X plus 1 is equal to 0. So x is equal to 5 or x is equal to -1. Now we have to check our domain. X must be greater than 1. So the only one that is valid is going to be x is equal to 5. Now let's do our final example. Let's say we have log base 2 x plus log base x, 16 is equal to 6. So first off, let's check our domain. For this, x must be greater than 0, and for log base x is equal x of input of 16, this must be x is greater than 0. So we also have that x cannot equal to 1. So we have this requirement and this requirement. Now let's use change of base on this part right here. We have log base 2 of 16 over log base 2 of x. So since we know that log base 2 of 16 is equal to 4, we could rewrite that, and we could rewrite this to say 4 over log base 2 of x is equal to 6. Log base 2 of x. And now we're going to use some u subs. So we're going to let u equal to log base 2 of x. So then you're going to have u plus 4 over u is equal to 6. So now you're going to multiply by u. So let's see here. If we have everything here multiplied by u and everything here multiplied by u, we get u squared plus 4. So this one cancels out. And we get 6u on this side. So because x cannot equal to 1, that means that log base 2x cannot equal to 0. Therefore, u cannot equal to 0. So what this means is we can just move the 6u over here. We have u squared minus 6u plus 4 is equal to 0. And we can just take the quadratic formula for here. 6 plus or minus the root of -6 squared minus 4 times 1 times 4. Okay, let's move this over a bit. All divided by 2. So u is equal to 6 plus or minus the root of 36 minus 16. All divided by 2. U is equal to 6 plus or minus the root of 20 divided by 2. This is 6 plus or minus the root of 2 times root 5, all over 2. And we have u is equal to 3 plus or minus the root of 5. So now we have to set u back to what it was defined as, which is log base 2 of x for the positive solution and the negative solution. So this is the positive solution, and this is our negative solution. So we can rewrite these exponentially. We have x is equal to 2 to the power of 3 plus the root of 5. And then here we have x is equal to 2 to the power of 3 minus the root of 5. So let's check our domain. Well, we can see that both of them are clearly positive. This is also positive as well. And neither of them are going to equal to 0 because of the fact that this here, it does not equal to 0. And this here, it does not equal to 0. So these are both going to be valid solutions. So this is going to be a solution. And also this is going to be a solution.